So I want to do some problems regarding equilibrium where the equilibrium constant is really large or really small. And I'll do some examples from OLI, and this is from page 68. So the first example I want to cover is the reaction between ammonia and water producing ammonium and hydroxide. The equilibrium constant for this reaction is pretty small, 10 to the minus fifth, 1.8 times 10 to the minus fifth. And I have laid out here the solution in an ICE table. So we start off with the initial concentration of ammonia is 0.25, and the initial concentrations of the products is 0. Just be mindful that 0 molar hydroxide is an approximation. We'll learn more about that when we get to acid-base chemistry. But for now, to simplify things, we'll just assume it's 0. So the change would be the loss of ammonia and the gain in ammonium and hydroxide. And because the stoichiometry is all 1 to 1, it's minus x here and plus x here and plus x here. So in the equilibrium line, we'll have 0.25 minus x and x here. Now, setting out the equilibrium constant expression, we'll have an x squared essentially in the numerator and 0.25 minus x in the denominator. If you leave this minus x in the denominator, you'll end up needing to solve a quadratic equation, which is, not impossible and, just takes a bit of time. But it turns out if the initial concentration is reasonably large relative to the equilibrium constant, if the equilibrium constant's really small, sometimes the difference here, the minus x, can be dropped or ignored, let's say, because the change in the concentration of the reactant, in this case the 0.25, will be negligible. Like this minus x will be pretty negligible compared to this initial amount. And this here is a way for you to help gauge if you could ignore this minus x. And that is if the initial concentration is greater than 100 times the equilibrium constant. If that's true, then you could ignore this minus x term. And so we go through the evaluation, and yes, the initial concentration, 0.25, is greater than 100 times the K. The K is 1.8 times 10 to the minus fifth. And so if you multiply that by 100, you'll get 0.0018, which is smaller than, of course, 0.25. So therefore, you could ignore the x, and that makes the algebra much simpler. So now you just simply cross-multiply and take the square root of that product. And then you have the answer for x, which is the concentration of the ammonium and the hydroxide. Next, I'd like to do an example on that same page in OLI. Here we have copper reacting with ammonia to form what is called a complex. In this case, it's a cation. So just real quick, these 4 ammonia molecules are somewhat covalently bonded, weakly covalently bonded to this copper ion. So because the ammonia is 0 charge, the positive 2 charge still remains. Anyway, so the equilibrium constant for this formation of this complex is really large, to the point where it's like it's a completion reaction. So keep that in mind. So I'll set up an ICE table as we would normally do. We would have the initial concentration of the copper 0.01 and the ammonia is 1, 0 for the product. Go through the steps of minus x, minus 4x. It's a 4x because of the coefficient 4 here, and then plus x. And then minus or 0.01 minus x in the equilibrium line, 1 minus 4x and x here. You set this up, and I don't have it all drawn out here, written out here, but if you were to write this out in the equilibrium constant setup, or the quotient, so to speak, you'd have x divided by these two. So you would have a binomial in the denominator. But this term here ends up being raised to the 4th power. So this is going to be a real complicated equation to solve. So in order to simplify this, maybe we could look at the equation or the chemistry in another way, and that is to say, hey, let's invoke a completion on this thing. So let's say all of this copper ion reacts and produces that same molarity amount of product, and we lose a bit of the ammonia in the correct stoichiometric amount. So that means we'll lose 0.01 here, and we'll lose 4 times that because it's a 4-to-1 ratio. And we'll make 0.01 molar of the product. We could sort of go in this direction or think the chemistry this way because the equilibrium constant is so big it's like really product favored. Okay, so why or how does this simplify our math? Well, let's continue and take a look, because this is going to be very complicated to solve. So let's see, the new initial concentration is going to be 0, 0.96 and 0.01. Now, this system is going to attain equilibrium. So the copper ion cannot be 0. We could imagine like we're invoking this 0.01 and 0.96 as our starting concentrations, which is fine. But we need to continue to solve this for equilibrium because this can't be 0. This has to be something. Now the forward reaction, as written, is highly product favored. Okay, so we cannot ignore the x. Unlike the previous problem, where the equilibrium constant was really small, and that would suggest very, very little ionization or forward reaction. Okay, very, very small equilibrium constants mean very little of your reactant is going to be consumed. On the other hand, here we have a very large equilibrium constant, so quite a bit of our is going to be consumed. And so if we leave this setup the way it is here, we cannot ignore the minus x as we did in the previous problem, or the minus 4x for that matter. So we need to leave these minus terms in there. And that's going to really complicate our algebra, because don't forget, here we have a 4, so this has got to be raised to the 4th power. All right, well, let's think of the chemistry in another way, and that is to invoke this completion. So we went through this, and so our new initial concentrations are going to be 0 for the copper, 0.96, and 0.01. Okay, if we think about this reaction in the reverse direction, okay, very little of this complex is going to ionize or break apart into its constituent components, because this thing is so darn product favored. So that means the amount of complex we're going to lose, like this minus x, is going to be really small. And for that matter, the amount of ammonia we're going to add back to the 0.96 is going to be also really small compared to 0.96. So then we could take a look at the reverse equilibrium constant, and that would be the inverse of the forward equilibrium constant. And so if we look at the equilibrium constant for the reverse reaction, it's really small, 2 times 10 to the minus 14th. And then we could go ahead and utilize that gauge, so to speak, to see if we could ignore this minus x going in the reverse direction, and the plus x for that matter also. So to see if that change is negligible. So we go ahead and ask the question, is the initial concentration of 0.01 and 0.96, are those two concentrations greater than 100 times the equilibrium constant? Because these concentrations are way greater than 100 times the equilibrium constant, the addition of the 4 and the loss of the minus x here is really negligible compared to these numbers. So that's justification for ignoring the plus 4x and the minus x. So now that really simplifies our math. So our equilibrium constant expression is going to be 0.01, and we're going to set it up in terms of product over reactant, using the original K value. Now that might seem a little confusing, but we're talking about the same chemistry, left to right. If we think of this reaction as left to right reactants and products, we could use this K, but we're going to substitute in these equilibrium values. And so we have 0.01 alone without that minus x, and then divided by x times this these two terms raised to the fourth power. Well, we could get rid of that plus 4x based on what I just said before. So now the math is simplified quite a bit. So now we have 0.01 over x times 0.96 raised to the fourth power, and solving for x is much easier. Okay, and so x is really small, as you can see, and we need to solve for x, of course, because we need to know what the copper concentration is, and that's what we have here. So the copper concentration is 2.35 times 10 to the minus 16th, and the concentrations of ammonia and the complex are just about where they were when we first started the reaction, so to speak, the initial concentration. So like if you were to add this number to 0.96, it's like nothing. Or subtract it from 0.01, it's like, so what, right? Anyway, that's a really slick way of simplifying your math, is if you look at the chemistry from the opposite angle or the opposite direction. Here's another problem from OLI and regarding a complex formed between nickel and ammonia. In this case, we have 6 nickel molecules coordinating, so to speak, or complexing with the nickel ion before it was copper. So the equilibrium constant for this is also large, 5.5 times 10 to the 8th. And we're going to approach it in the same manner as before, sort of invoking this completion reaction, because if we don't think of this as a completion reaction, we kind of approach it in the customary way where we have these initial concentrations of 0.25 molar nickel and 2 molar ammonia, we're going to need to solve for the minus x, so to speak, and that would really complicate the math, because now we have a raised to the 6th power. That's like super crazy, right? So imagine that if you had to do like 2 minus x and 0.25, or sorry, 2 minus 6x and 0.25 minus x, and then raise that to the 6th power, and this would be like x, and go through the whole algebra in sort of the customary way. That would be really, really challenging. So, not even wanting to write that out because it sounds like really stressful, let's just look at this in terms of a completion reaction. So you could even go right into these problems and say, hey, look, man, this thing is really big. Let's invoke completion. If this is kind of what you're starting with the initial concentrations of the reactants, say invoke completion and go from there. And so we'll just go right to that and say, okay, we initially have 0.25 and 2, so we're going to invoke completion and say, all right, we're going to consume all this and transfer that to the complex. And so now we're going to say our initial complex concentration, rather than this being the initial starting point, we're saying the initial starting point is the complex and some amount of ammonia. Okay, so we're conserving mass. It's not like we're making up something mysterious to this chemistry. We're conserving the mass that the original problem is providing. So we're just kind of shifting it around among the reactants and the products, and we're doing it in a legally stoichiometric manner, and we're not making anything up. We're just following the chemistry that what we have here with the amounts that we are starting with. We're just playing a clever little, we're taking a clever approach to this, is really what it is. So anyway, let's start with 0.25 molar complex and or product, and let's start with 0.5 molar ammonia and 0 nickel ion. And let's say the equilibrium reaction starts like this, and it needs to attain equilibrium from these points, or from these starting amounts. So then, okay, minus x, and I forgot to put the 6, I just noticed that here, 6x, and plus x here. And then equilibrium line, we need to bring down this x, and this we cannot ignore. This can't be 0, or else we won't have any concentration of nickel. So this has to be our x, so to speak. And then we have the 0.5 plus the 6x and 0.25 minus the x. Okay, we'll put that in the line item for equilibrium. I have redded out the 6x and the x because we're going to ignore them. And that's because the equilibrium for the reverse reaction is really, really negligible, because this is so highly product favored that the amount of, like before in the previous problem, like the amount of complex that's going to break up into its constituent components is going to be really small, because the K for the reverse reaction is like 10 to the minus 9th, 1.82 times 10 to the minus 9th. So we could go through that check of saying, okay, the initial concentration of complex, let's say, is way greater than 100 times K reverse. So we're justified in saying, yeah, this minus x is going to be real tiny, and then this plus 6x compared to the 0.5 is going to be like negligible. So that really simplifies the math. So now we have 0.25 divided by the product, 0.25, divided by the two reactants, x, and now 0.5 raised to the 6th power. Don't forget, there's that 6 there, so we need to take that into account in the quotient. And so the algebra is pretty easy now. We solve for x and raise that 0.5 to the 6th power, and we end up with a really small value for nickel. And that's what we would expect based on the reverse equilibrium constant.